Morning, all of you. My name is B. Srinivasulu, Department of Mechanical Engineering. Today, I am going to the hydraulic turbines. This is the unit number 4, mechanical second years and second civil second years common topic. Okay, unit number 4, hydraulic turbines. Last before videos, I can explain the what is the turbine, define turbine, what is the working principle of the turbine, and the classifications of the turbines already explained. Okay, turbine is a the conversion of water energy into the mechanical energy. Okay, already explained the turbine definition and classifications of the turbines. So impulse turbine, reaction turbine, next the radial turbines, tangential turbines, axial turbines, and mixed flow turbines. Next, high head turbines, low head turbines, medium head turbines, high speed turbines, low speed turbines, medium speed turbines, also classifications of the turbines. Next, impulse turbines, reaction turbines. Impulse turbines is a Pelton wheel turbine. Already I can explain the Pelton wheel turbine and working of the Pelton wheel turbine and efficiency of the Pelton wheel turbine and solve the small problems on Pelton wheel turbines. And Francis turbine. Francis turbine and also explained last before classes. So Francis turbine is a reaction turbine. So the work done of the Francis turbine and small problems on the Francis turbine. Today I am going to the Kaplan turbine. Kaplan turbine is a one type of a reaction turbine. Okay, propeller turbine or Kaplan turbine. This is the one type of a reaction turbine. In this turbine, we can explain the work done of the Kaplan turbine and small problems on the Kaplan turbines. Okay, in this video, drop tips, different types of drop tips. Okay, now what is the purpose of the drop tips and the characteristic curves of the turbines. Okay, propeller turbine. The need to utilize low head. Okay, the need to utilize low head where large volume of water is available makes it essential to provide a large flow area and to run the machine at very low speeds. Okay, the propeller turbine is a reaction turbine used for heads between 4 meters to 80 meters. Okay, the reaction turbines are propeller turbine is a reaction turbine. In this reaction turbine, this turbine head between 4 meters to 80 meters. The head between 4 meters to 80 meters. This is a low speed turbines. Okay, low speed turbines and low head turbines. Okay, 4 meters to 80 meters. It is purely axial flow device providing a large largest possible flow area that will utilize a large volume of water and still obtain flow velocities which are not too large. Okay, in this turbine, the flow velocities are not too large. Okay, the propeller turbine, as shown in the figure, consists of an axial flow runner with 4 to 6 are at the most 10 blades of airfoil shape. Okay, in this turbine arranged in 4 to 6 blades. Okay, the runner is generally kept horizontal. In this turbine, runner is arranged in the horizontal. Next, that is the shaft is vertical. Okay, shaft is vertical. The blades reassemble the propeller of a ship. Okay, the propeller turbine in Francis turbine, the runner blades are fixed and not adjustable. Okay, propeller turbines blades are fixed, not adjustable. Okay, the spiral casing and guide blades are similar to the those Francis turbines. The guide mechanism is similar to that of the Francis turbine. Okay, Francis turbine, Kaplan turbine also, propeller turbine also, reaction turbines. Okay, Pelton wheel turbine is a impulse turbine. In this guide mechanism and spiral casing, both are same reaction turbines. In Francis turbine and propeller turbine and Kaplan turbines. Propeller turbine means a Kaplan turbine. This is the Kaplan turbine. This is a Kaplan turbine. In this, as shown in the figure. Okay. First figure one shaft and scroll casing. Okay, runner vane and guide vane and draft tube, tail race and hub. These are the main parts of the Kaplan turbine. These are the main parts of the Kaplan turbine. Next, as shown in the figure, bottom figure, guide vanes, runner and water inlet from the penstock. Water inlet from the penstock. Ante water is taken into the penstock. Okay. The guide vanes and runner vanes are arranged in the blades. Okay, guide vanes or runner vanes are the small parts of the Kaplan turbine. These parts are as same as the Francis turbine. Okay, hub. Hub is the separate part. Okay, separate. We can draw the separate figure. You can understand hub, shaft, vanes. Vanes are horizontal. Next shaft is a vertical connection. Okay, this is the total Kaplan turbine figure. In this Kaplan turbine is axial flow reaction turbine. In this Kaplan turbine is axial flow reaction turbine, which was developed by Australian engineer V. Kaplan. Okay, it was developed by Australian engineer V. Kaplan. Because of the name of the turbine is Kaplan turbine is a scientist name. Okay, Kaplan means is a scientist name. Okay, it is suitable for relatively low heads. Okay, in this turbine mostly used in places. Okay, low head places. Okay, hence it requires large quantity of water to develop large power. Okay, because of in this turbine is a low head turbine, but large quantity of water to develop large power. Okay, in this turbine, large power is developed and large quantity of water is taken. Okay, Kaplan turbine is a low head turbine, so because of large quantity of water to deliver to develop large power in this turbine to develop a large power. Next, in this main parts, scroll casing, okay, na, guide vanes, runner, and draft tube. Draft tubes are used in only reaction turbines. In this part, ante draft tube is not used in Pelton wheel turbines. The draft tubes are used in mostly in reaction turbines. Okay, draft tube is a additional component. Okay, additional component. Okay, in this turbine the arrangement of above components are similar to the those Francis turbine. Okay, all components are same in the Francis turbine. All components are same in the Francis turbine. Okay, Francis turbine components and Kaplan turbine components are same. Okay, the runner blades are adjustable and can be rotated about pivot fixed to the hub of the runner. Okay, the runner blades are rotated. Okay, na the runner blades are attached to the hub. Okay, next, usually it has 4 to 6 blades having no outside rim. Okay, 4 to 6 blades are having. Next, the shape of the runner blade. Okay, the shape of the runner blade is different from that of Francis turbine. Okay, the shape of the runner blade is different from that of Francis turbine. The blades are made up of stainless steels. The blades are made up of stainless steels. The blades attached to the hub are so shaped that water flows axially through the runner. Okay, axially to the runner. This is the um, Kaplan turbine. Okay, na? Next. Okay, this is a small problem on Kaplan turbines. Okay, a Kaplan turbine develops a Kaplan turbine develops 22,000 kilowatts at a arranged head of 35 meters, assuming a speed ratio of to flow ratio of 0.6 diameter of the boss equal to the 0.35 times of the diameter of the runner and an overall efficiency of 88%. Calculate the diameter, speed and specific speed of the turbine and specific speed of the turbine. This is a Kaplan turbine, small problem. First of all, to write down the given data. Okay, in this problem, to given the shaft power. Okay, P equal to 22 kilowatts, head H equal to 35 meters, speed ratio Ku equal to 2.0, flow ratio Kf equal to 0.6. Speed ratio symbol is Ku. Okay, flow ratio symbol is Kf. Okay, next diameter of the boss. Diameter of the boss dB equal to 0.35 into diameter of the runner d naught, that equal to dB equal to 0.35 d naught. This condition is given in the problem. Next, the overall efficiency equal to 88%. The overall efficiency equal to 88%. Next, to determine the diameter of the runner. Okay, to determine the diameter of the runner d naught. Therefore, Ku equal to u1 by root of 2gh. This is the formula of speed ratio. Okay, Ku equal to u1 by root of 2gh, that equal to Ku already given in the problem and 2.0. In this equation, u1 equal to 2.0 into root of 2gh. Therefore, 2.0 into root of 2 into 9.81 into head means 35. That values are substituted in this equation to calculate the u1 value is 52.4 meter per second. Next, Kf. Kf means flow ratio. Kf equal to Vf1 by root of 2gh, that equal to 0.6, or Vf1 equal to 0.6 into root of 2gh. Therefore, the Kf value is 15.7 meter per second. Next, overall efficiency. Overall efficiency means shaft power by water power. Overall efficiency means shaft power by water power. Okay, this is a hub. Okay, na runner, boss, dB, d naught. Okay, dB are given in the problem, d naught are given in the problem. Okay, that condition is available in the problem. dB equal to 0.35, d naught. Okay, overall efficiency equal to shaft power by water power. Shaft power is also given in the problem 22,000. Okay, water power means WQH. Water power means WQH. Okay, the overall efficiency is already given in the problem, that equal to 0.88 equal to 22,000 divided by 9.81. Okay, into Q into 35. Okay, therefore Q equal to 22,000 divided by 0.88 into 9.81 into 35, that equal to 72.8 meter cube per second. Okay, therefore Q equal to area of flow into velocity of flow. Area of flow into velocity of flow. Okay, that equal to pi by 4 into d naught square minus dB square into Vf1. Okay, d naught square into dB square into Vf1. Okay, Q equal to 72.8, that equal to pi by 4 d naught square minus dB 0.35 dB d naught whole square into 15.7. Okay, that equal to pi by 4 d naught square into 1 minus 0.35 square into 15.7, that equal to, in terms of d naught, 10.82 d naught square. Therefore, d naught equal to 72.8 divided by 10.82 whole to the power of 1 by 2, that equal to 2.6 meters. D naught value is the 2.6 meters. Next, speed of the turbine N. Okay, speed of the turbine N. U1 equal to pi dn by 60. Un equal to pi dn by 60. Therefore, N equal to 60 U1 by pi d naught. That equal to 60 into 52.4 divided by pi into 2.6. That equal to 384.9 RPM. Next, specific speed of the turbine. Specific speed of the turbine N, Ns. Okay, specific speed of the turbine Ns. Ns equal to N into root P by H power of 5 by 4. That equal to N is the already calculated in the value, that equal to 384.9 into P is the power is available in the problem 22,000 divided by H35 whole to the power of 5 by 4. In this equation to calculate the Ns, that equal to 670.6. Okay, next, this is a another problem of the problem in this unit 2. Okay, fluid mechanics and hydraulic missions subject to in this unit 2, small definitions and mostly important in problems. Okay, in external examinations, mostly important to asked in problems. Okay, the propeller reaction turbine, the runner diameter 4.5 meters is running at 48 rpm. The guide blade angle at inlet is 145 degrees and the runner blade angle at outlet the runner blade angle at outlet is 25 degrees to the direction of vane. Okay, the axial flow area of water through the runner is 30 meter square. If the runner blade, the angle at inlet is radial, determine hydraulic efficiency of the turbine discharge to the turbine, power developed by the turbine. Okay, first of all, to write down the given data, diameter of the runner d naught equal to 4.5 meters. Okay, speed of the runner n equal to 48 rpm. Okay, guide blade angle alpha equal to 145. Runner blade angle at inlet radial theta equal to 90. Vf1 equal to Vr1. Okay, runner blade angle at outlet pi equal to 25. Area flow AF equal to 30 meter square. This is the figure. Okay, as shown in the figure, and this is the velocity figure, hydraulic efficiency of the turbine. Okay, now this is the velocity of the Kaplan turbine figure. Okay, in this portion is inlet velocity triangle. In this inlet velocity triangle equal to Vf1 equal to Vr1. There is that equal to theta equal to 90 degrees because of Vf1 equal to Vr1. Next, the alpha is the velocity angle. Okay, inlet velocity angle. U1 equal to VW1 into velocity of flow and variable velocity, that equal to same. And next, the direction of the motion. Next, the runner vanes, the outlet velocity triangles in VF2 and V2 and VR2 pi equal to 25, U2 and VW2 beta. In this velocity triangle, we can calculate the all values in this problem. Okay, in this diagram, alpha equal to 145, theta equal to 90 degrees. Okay, therefore Vf1 equal to Vf2 because of the area flow is constant. Because of the area flow is constant, the water flow is, the water velocity is constant. Next, the tangential speed of a turbine at inlet U1 equal to pi dn by 60. The tangential speed of turbine at inlet. Okay, inlet means U1 equal to pi dn by 60, pi into d naught. Okay, pi into d naught, n equal to already given in the problem divided by 60, that equal to 11.31 meter per second. Okay, velocity. Next, Also, U1 equal to U2 that equal to 11.31 meter per second. From inlet triangle, ante from inlet triangle, from the diagram to calculate the values. From inlet triangle, tan 180 minus alpha equal to Vf1 by U1. In this formula is taken from the uh, velocity triangle diagram, from inlet triangle diagram. In this angle is theta, theta. Okay, tan 180 minus alpha equal to tan 180 minus alpha equal to Vf1 by Vr1, Vf1 by U1. Okay, this is the Vf1 by U1 equal to tan theta. Tan theta means 180 minus alpha equal to theta. Okay, in this inlet diagram, tan 180 minus theta equal to Vf1 by U1. Therefore, that equation you can calculate the Vf1, Vf1 equal to U1 into tan 35, that equal to 11.31 meter per 7.992 meter per second, 7.92 meter per second. Vf1 equal to U1 into tan 35, that equal to Vf1 value. Next, therefore, Vw1 equal to U1, that equal to 11.31 meter per second. From outlet triangle, tan pi equal to Vf2 by U2 plus Vw2, that equal to Vf2 equal to Vf1, U2 equal to U1. In this, tan pi equal to Vf2 by U2 plus Vw2 equation to calculate the Vw2, tan 25 equal to 7.92 divided by 11.31 plus Vw2. Okay, therefore Vw2 equal to 16.98 minus 11.31, that equal to 5.67 meter per second. Next, V2 equal to root of Vf2 square plus Vw2 square, that equal to 9.74 meter per second. Next, H equal to 1 by G Vw1 U1 minus Vw2 U2 plus V2 square by 2G. Negative sign is taken since the absolute velocities at inlet and outlet is the same direction and are the velocities of viral. Velocities of the viral. H equal to 1 by G means 9.8 into 11.31 into 11.31 minus 5.67 into 11.31 plus 9.74 whole square by 2 into 9.81, that equal to 6.5 plus 4.83, that equal to 11.33 meters. Okay, H equal to head. Next, hydraulic efficiency equal to Vw1 U1 minus Vw2 U2 divided by GH. Okay, Vw1 11.31 into 11.31 minus 5.67 into 11.31 divided by 9.81 into 11.33, that equal to 0.575. Okay, or 57.5%. Okay, this is the hydraulic efficiency of the turbine. Next, discharge through the turbine. Discharge through the turbine. Q equal to area flow into velocity of flow. Area flow is means AF. Velocity of flow means VF1. Okay, area flow that equal to 30 and velocity of flow of VF1 equal to 7.92. That value is calculated to 37.6 meter per second. Okay, this is the discharge value. Next, power. Power developed by the turbine equal to WQ by G into VW1 U1 minus VW2 U2. This is the formula of the power developed. Okay, W equal to weight of the water, 9.81 into 237.6 by 9.81 G. Okay, UW1, U1 and minus VW2 U2 values are substituted in this equation to calculate the power developed by the runner, that equal to 1515 kilowatts. Okay, this is the problem. Next topic is draft tube. Next topic is draft tube. In this reaction turbines are used in the one part of draft tube. In case of mixed and axial flow turbines, only a part of available energy is converted into the velocity energy. Energy is converted into the available energy is converted into the velocity energy at the inlet of the runner. Okay, the rest is in the form of pressure energy. This radial pressure is converted into velocity in the runner, as a consequence of which the outlet velocity increases. Okay, with the increase in the value of specific speed ns, the exit velocity energy v2 square by 2g increase compared with h, or available energy. In Pelton wheel, all the available energy is converted into the velocity energy before it is striking the wheel. Okay, in Pelton wheel, all the available energy is converted into the velocity energy before the striking the wheel. In such works, under atmospheric conditions, the wheel has to be placed above the maximum tail race level. The loss of energy due to exit velocity varies from 1.44 percentages. అంటే some available energy losses are available energy losses in the turbines, that energy losses are 1 to 4%. Next, draft tube theory. This is the most important theory, draft tube theory. Okay, consider a draft tube is fixed with a consider a turbine fitted with a draft tube. Okay, a draft tube means a conical part. Okay, let y equal to distance from the bottom of draft tube from the tail race. Okay, y equal to distance from the bottom of draft tube from tail race. PA equal to atmospheric pressure at the surface of the tail race. PA means atmospheric pressure. Okay, na? Next, applying Bernoulli's equation, section 3.3 and section 2.2. Okay, in this draft tube, okay, conical shape. Okay, turbine casing. Okay, na? Next, part 2 and part 3. This is divided into the part 2 and part 3 by applying of a Bernoulli's equation. Part 2 and part 3 is equating. Okay, next, P2W P2 by W plus V2 square by 2G plus Y2 equal to P3 by W plus V3 square by 2G plus O the plus HF. HF means head losses due to the friction in the part 3, and 0 Y3 means there is no datum head. Okay, from tail race to drop tube end point, there is no height. Okay, Y2 is the height of the drop tube from bottom to the second portion. Okay, next. Okay, P2 by W equal to P3 by W minus Y2 minus V2 square minus V3 square by 2G minus HF. Okay, substituting the P3 by W equal to PA by W plus Y. E PA means atmospheric. Okay, na? Atmospheric pressure. Therefore, the equation is written as P2 by W equal to PA by W plus Y minus Y2 minus V2 square minus V3 square by 2G minus HF. The term y2 minus y, which represents the vertical distance from the runner, exists. The tail water level is called section head of draft tube. Section head of the draft tube means y2 minus y. It is denoted by hs. Okay, na? Corresponding the factor v2 square minus v3 square by 2g is called dynamic head. Okay, ante means velocity head. Therefore, the equation is P2 by W that equal to PA by W minus HS minus V2 square minus V3 square by 2G minus HF. In this equation, P2 by W is less than atmospheric pressure. Okay, na? The efficiency of a dropped tube means it is defined as the ratio of net gain in pressure head to the velocity head at entrance of the dropped tube. The ratio of net gain in pressure head to the velocity head at entrance of draft tube. Therefore, the efficiency of the draft tube equal to net gain in pressure head divided by velocity head at entrance of the draft tube. Net gain pressure head means V2 square minus V3 square by 2g minus HF divided by V2 square by 2g. The velocity head at the entrance of the draft tube. Vt equal to velocity of water at section 2 to inlet of the draft tube. V3 equal to velocity of the water at section 3 outlet of the draft tube. Okay, na? Therefore, HF equal to V2 square minus V3 square by 2g minus efficiency D into V2 square by 2g. Okay, this is the equation of HF and the efficiency equation of draft tube. Efficiency means V2 square minus V3 square by 2g minus HF by V2 square by 2g. Okay, HF equal to, in this equation, HF equal to V2 square minus V3 square by 2g minus efficiency D draft tube into V2 square by 2g. In this equation written as a HF. Okay, next, types of draft tubes. This is the most important topic. Types of draft tubes. Okay, in this draft tubes are available in the reaction turbines, mainly four types. First one is the conical draft tube. Okay, simple elbow draft tube, Modian spreading draft tube, and elbow draft tubes with circular inlet and rectangular outlet. Okay, as shown in the figures. First one is the conical draft tube. అంటే the shape, అంటే depending upon the shapes, we can classify it into the four types. Okay, conical draft tube and simple elbow, తర్వాత modi and spreading, and draft tube with circular inlet and rectangular outlet draft tubes. These are the most important draft tubes and figures. Next, specific speed. This is the important small definition. Specific speed of a turbine defined as the speed of turbine which is identical in shape, geometrical dimensions, blade angles, gate opening, etc., which would develop unit power when working under a unit head. Okay, the specific speed may be derived as follows: the overall efficiency not of any turbine is given by power available at the shaft of the turbine, means shaft power by water power supplied at the inlet of the turbine. Therefore, the equation equal to shaft power P and water power W KH. In this equation, P equal to shaft power, Q equal to discharge through turbine, H equal to head under with the turbine is working, W equal to weight density of water, P equal to power P equal to efficiency into WQH. EP. Therefore, P means we can written as a equation number 1, P equal to efficiency into WQH. P proportional to Q proportional to P proportional to Q into H. Okay, the efficiency and W are constants. D is the diameter of the actual turbine. N is the speed of actual turbine. U is the tangential velocity of turbine. Ns is the specific speed of the turbine. V is the absolute velocity of the turbine. The relationship V, U, and H is the given below. V proportional to V, where V proportional to root H. That is the U proportional to root H. Okay, therefore the velocity U equal to pi dn by 60. Therefore, root H equal to root H proportional to dn. D equal to root H by n. Okay, therefore Q equal to area into velocity. Area is proportional to B into D. D is means width. Therefore d square. Okay, q proportional to d square into root h. Therefore root h by n whole square into root h. Okay, na, in this equation is written as, okay, na, p proportional to h power 3 by 2 by n square into h proportional to h power of 5 by 2 by n square. Therefore p equal to k into h power of 5 by 2 by n square, where k is the constant proportionality where P equal to 1 kilowatts, H equal to 1 meters, speed equal to ns. Substituting these values are in the above equation, 1 equal to K into 1 power of 5 by 4 into ns square. Therefore, K equal to ns square. The K value is substituted in the P equal to K into h power of 5 by 2 divided by n square. Okay, na? Therefore, the equation is written as ns equal to n into root P by h power of 5 by 4, where P is the kilowatts and h is the meters. Therefore, small problems on the turbine. Okay, a turbine is operate under a head of 25 meters at 200 rpm. The discharge is 9 meter cube per second. If the overall efficiency equal to 90% of turbine. Okay, to determine the power generated, specific speed of the turbine, type of turbine. Okay, h equal to 25 meters. Okay, h equal to 25 meters. H equal to 25 meters, speed equal to 200 rpm, discharge equal to Q, overall efficiency equal to 90%. The power generated P equal to efficiency into WQH. Okay, efficiency means 0.9. Okay, na W means 9.81, Q equal to 9, and H equal to 25. That value is 1986.5 kilowatts power. Specific speed N is equal to N root P by H power of 5 by 4. This is the turbine specific speed. N value is already given in the problem and P value is already calculated in the problem. H value is already given in the problem. All values are substituted in this equation to calculate the NS equal to 159.4 rpm. Okay, type of a turbine. The specific speed between 80 to 400. The specific speed is between 80 to 400. The turbine is Francis turbine. Okay, 80 to 400. That means the turbine is a Francis turbine. Next, main characteristics curves. Main characteristics curves. These are the characteristics curves, and head and gate operating are maintained constant. The speed is by allowing a variable quantity of water to flow through the inlet opening. The brake power P is measured mechanically by means of a dynamometer. The overall efficiency and unit quantity are the calculated by using of basic data. These are the plotted against unit speed versus aspesa. Okay, na? In this figure, first figure is to draw the figure. First figure, gate value opening 1.4, 1.2, 3.41. Okay, gate value is opening ranges. So, okay, in this figure, to draw the figure, discharge versus speed. Next, power versus speed. Next, efficiency versus speed. Okay, na? Discharge versus speed, gate opening value is straight lines. Okay, horizontal lines. Ante the speed is a constant. Okay, na? The speed and discharge is a constant. Okay, na? Next, power versus speed figure. The gate value is opening 1.4, 1.4, 1.2, 3.4, 1. This is the one characteristic curve. So you can draw the origin point to some maximum value. Next, it is reducing lines. Okay, na? Next, as same in the efficiency and speed values. Next, the main characteristics curves of a Francis turbine. These are the Pelton wheel turbine. Next, these are the main characteristics curves of a Francis turbines. Okay, na? The main characteristics curves will following the information. First figure is discharge versus speed. Next is power versus speed. Next is efficiency versus speed. Okay, na? First figure is also draw the discharge versus speed figure. The discharge values are the gate value is opening 1.4, 1.2, 3.4, 1.0. Okay, these figures are already explained in the civil department unit number 5, pumps. Okay, pumps, centrifugal pumps also characteristics curves are available. In this turbine also characteristic curves are available. Okay, in this turbines, Pelton wheel, Francis, Kaplan. Okay, Kaplan turbine is not mentioned in your syllabus, civil department. Okay, in civil department only Pelton wheel and Francis turbines are available in your syllabus. Next, drop tubes also available. So, okay, in this main characteristics curves as following information: the discharge versus a Pelton wheel depending upon the gate opening and different speeds, and the curves of QU are horizontal lines. The curves between discharge and speed for the Francis turbine are falling curves. Okay. Next, as a centrifugal head develops, which acts outward and opposite to the external head causing flow. Okay. The curve between discharge versus speed, a Kaplan turbine are rising curves. Okay, Kaplan turbines also rising curves. Pelton wheels also straight lines depending upon the curves are horizontal lines. Okay, na Francis turbine curves also falling lines. Okay, both three turbines curves. Okay, na both three three turbines curves. First Pelton wheel, Francis, Kaplan. Pelton wheel turbines the main characteristic curves are horizontal lines. Okay, na? Next, Francis turbines, the curves are falling curves. Okay. Next, Kaplan turbines means the curves are rising curves. Okay, na? Three important points. In these curves are Kaplan turbine curves. Okay, na? The curves between power versus speed, those between efficiency and speed indicate a particular speed. The efficiency is maximum. Okay, efficiency is maximum in power versus speed curves and efficiency versus speed curves as shown in the figures. Second figure and third figure, the efficiency sometimes are high అంటే maximum value are sometimes next falling, first rising and some maximum value is to reach the curve, next falling the curve in both power versus speed curve and both next efficiency versus speed curve. Next, this is the small chart. Okay, small chart of the turbines. First, Pelton wheel, Francis, Kaplan. Okay, Pelton wheel 1 jet, 2 jets, 4 jets are available. Francis lo high head, medium head, low head. Okay, propeller and Kaplan turbines also high head, medium head, low heads are available. Okay, first Pelton wheel head up to 2000, up to 15,000, up to 5,000. అంటే 4 jets means up to 5,000 head. Next 2 jets means up to 1,500 head. Next 1 jet means 2,000. Okay, head. Next specific speed of the turbines. Pelton wheel 1 jet means 12 to 30 rpm. 2 jets 17 to 50 rpm. Next 4 jets 24 to 70 rpm. Next Francis turbine 80 to 150, 150 to 250, 250 to 400. These are the high head, medium head, low head. Okay, now speeds are low speed, medium speed, high speed. In this chapter, sorry, in this slide, the turbines are three types: Pelton wheel turbine, Francis turbine, and Kaplan turbines. Okay, na? In this figure, Francis turbine, high head turbine, medium head turbine, low head turbine. Okay, high head turbines are having low speeds. Okay, medium head turbines are having medium speeds. Low heads are having high speeds. Okay, na opposite to high head turbine and low speed. Medium head turbine, medium speed, and low head turbine, high speed. Okay, na? Next, surge tank. It is a small component. Surge tank. Surge tank is a small reservoir. Okay, or tank in which the water level rises or falls to reduce the pressure sieving to the. They are not transmitted in full to closed circuit. In general, surge tank is employed or following purpose to produce the discharge, no, to produce the distance between the free water surface and turbine, thereby reducing the water hammer effect. Okay, water hammer effect means the change in pressure rapidly above the below normal pressure caused by the sudden changes in the rate of flow through the pipe according to the demand of the prime mover. Okay, అంటే engine లోకి water, అంటే prime mover means a machine which generate power by utilizing some form of energy is called a prime mover. ఓకే, ప్రైమ్ మూవర్ లోకి వాటర్స్ ని ఎంటర్ అయ్యేటప్పుడు ఎలాంటి చేంజెస్ లేకుండా వాటర్ ని ఎంటర్ చేస్తూ ఉండేదాన్ని సర్జ్ ట్యాంక్ అంటాం. ఓకేనా. నెక్స్ట్, the types of surge tanks. This is the hydroelectric power station figure. First part is a dam. Okay, next part is a reservoir అంటే water levels. Next, penstock, surge tank and power. In reservoir, okay, means the storing the water. Dam means we control the water అంటే to living into the water అంటే క్యూసిప్స్ అంటే వాటర్ ని ఎంత లెవెల్లో రిలీజ్ చేయాలో యూజ్ చేసేదానికి డ్యామ్ యూజ్ చేస్తారు. అక్కడ వాల్యూస్ ఉంటాయి. ఓకేనా. రిజర్వాయర్ నుంచి వాటర్ అనేది పెన్ స్టాక్ లోకి ఎంటర్ అవుతుంది. పెన్ స్టాక్ నుంచి పవర్ హౌస్ లోకి ఎంటర్ అవుతుంది. అక్కడ ఏముంటుంది, టర్బైన్ ఉంటుంది. ఈ వాటర్ ఎనర్జీ అక్కడ మెకానికల్ ఎనర్జీగా కన్వర్ట్ అయ్యి మెకానికల్ ఎనర్జీ ఎలక్ట్రికల్ ఎనర్జీగా కన్వర్ట్ అయ్యి స్టోర్ అవుతుంది. ఈ సర్జ్ ట్యాంక్ మీన్స్ ఏంటంటే ఇప్పుడు వాటర్ అనేది పెన్ స్టాక్ లో నుంచి టర్బైన్ కి ఫ్లో అవుతా ఉంటాయి. ఈ సర్జ్ ట్యాంక్ వల్ల ఈ సర్జ్ ట్యాంక్ లో సమ్ వాటర్ అనేది స్టోర్ అయ్యి ఉంటాయి. ఇప్పుడు రిజర్వాయర్ నుంచి వాటర్ లెవెల్స్ డౌన్ అయినప్పుడు సర్జ్ ట్యాంక్ ఏం చేస్తుందంటే ఆ వాటర్ లెవెల్ ని ప్యూరిఫై చేస్తుంది, అంటే ఫుల్ఫిల్ చేస్తుంది. ఆ వాటర్ లెవెల్ ని ఫుల్ఫిల్ చేస్తూ టర్బైన్ మీదకి వాటర్ ని ఫ్లో చేస్తూ ఉంటుంది. ఓకేనా. నెక్స్ట్, cavitation factor. This is the most important topic. In cavitation factor, in cavitation factor sigma c. Okay, na sigma c equal to ha minus hv minus hs by h. This is the equation is most important too, where ha atmospheric pressure head meters of water. Okay, hv vapor pressure in meters of water corresponding to the water temperature. Next, h equal to working head of turbine. Okay, difference between head race and tail race level in meters. HS is the suction head. Okay, the values of critical factor depends upon the specific speed of the turbine. Next, unit quantities. Unit quantities are most important to only formulas. Unit quantities are most important to only formulas. Unit quantity means root h by root h. Okay na. This is the unit quantity. Ante some water is available in head. Okay, u dash, q dash, p dash. U means total velocity. U dash means some velocity అంటే per water, అంటే per second, per meter, per hour based. ఓకేనా. నెక్స్ట్, in this equation v equal to absolute velocity, vr equal to relative velocity, u equal to peripheral velocity. v dash, ur dash, u dash corresponding values are different heads h dash. Then the velocities are proportional to the root h. We have u by u dash, vr by vr dash, v by v dash equal to root h by root h dash, as per same as the discharges. q by q dash, v by u dash, n by n dash, root h by h dash. Next, power also same, p by p dash and qh by q dash h dash, root h by root h dash into h by h dash. These are the same, అంటే total power divided by unit quantity of power. Total power divided by unit quantity of power. Total discharge per unit quantity of discharge. Total velocity per unit quantity of velocity per unit measured. Next, the hydraulic efficiency of a turbine under these two heads may be considered. Okay, the velocity triangles, these heads are similar. Okay, in this, if the various quantities are reduced to a theoretical 1 meter head comparison of a performance data and computations of experimental values on the single unit, okay, are considered by. This is the unit speed, unit discharge, unit power equations. These equations are most important. These equations are unit quantities. Okay, unit speed means n by root h. Unit speed means n by root h, and based upon the head. Unit speed means n by root h. Unit discharge means q by root h. Unit power means P by h power of 3 by 4. Okay, h power of 3 by 4. These three equations are most important. The above quantities are called unit quantities. Okay, na? Unit speed, unit discharge, unit power. Okay, these are the unit quantities. Next, already I can explain the turbine. What is a turbine? Okay, na, working of a turbine. The turbine means the hydraulic energy is converted into the mechanical energy. Most important. Okay, na? The turbine means hydraulic energy is converted into the mechanical energy. In this chapter, hydraulic turbines chapter, what is a turbine? Okay, define turbine. Classifications of turbines. Classifications are according to the water flow, impulse and reaction. Next, according to the main direction of flow. Okay, tangential flow, radial flow, axial flow, mixed flow. Okay, next head, based on the head, high head, medium head, low head. Next speed, high speed, low, medium speed, low speed. These are the classifications of the turbines. Okay, na high head turbines means Pelton wheel. Okay, medium head turbines means Francis turbine. Low head turbine means Kaplan turbine. Okay, same as the low speed Pelton wheel. Okay, medium speed Francis. Okay, high speed Kaplan. These are the most important topics. Okay, classifications of a turbines and define a turbine. Next, Pelton turbine. Pelton turbine యొక్క work done equations. Okay, na small problems on the Pelton wheel. Next, Francis turbine. Francis turbine work done equations. Next, small problems on the Francis turbine. Next, Kaplan turbine. Kaplan turbine only in mechanical syllabus. Okay, Kaplan turbine not considered in the civil syllabus. Okay, na Kaplan turbine working principle and small problems. Next, draft tubes. Draft tubes are civil and mechanical combined topic. Draft tube, different types of draft tube. What is the purpose of draft tube? Okay, na draft tube theory. Okay, these are the topics. Draft tubes are four types. Okay, na modi and spread, simple elbow, and inlet of the circular section, outlet of the rectangular sections are four types. Okay, draft tubes are four types. These are the important small answer question. Next, surge tank. Surge tanks are used in the hydroelectric power stations or hydroelectric stations. The surge tank used to fulfill the water into the turbines. Okay, na? అంటే రిజర్వాయర్ నుంచి వాటర్ అనేది పెన్ స్టాక్ నుంచి టర్బైన్ బ్లేడ్ మీద ఫ్లో అయ్యేటప్పుడు వాటర్ లెవెల్స్ ఏమన్నా డిక్రీజ్ అయినప్పుడు సర్జ్ ట్యాంక్ నుంచి వాటర్ లెవెల్ తీసుకొని టర్బైన్ మీదకి ఫ్లో చేస్తాయి. మెయిన్లీ ఇన్ దిస్ చాప్టర్ the power generated purpose. Okay, the hydraulic energy is converted into the mechanical energy, mechanical energy is converted into the electrical energy. Okay, these are the main purpose. Next, already explained the pump means mechanical energy is converted into the hydraulic energy. Okay, turbine means hydraulic energy is converted into the mechanical energy. Both are the opposite. Pump ఏమో మెకానికల్ ఎనర్జీని హైడ్రాలిక్ ఎనర్జీగా కన్వర్ట్ చేస్తుంది. ఓకేనా, టర్బైన్ ఏం చేస్తుంది, హైడ్రాలిక్ ఎనర్జీని మెకానికల్ ఎనర్జీగా కన్వర్ట్ చేస్తుంది. ఈ టర్బైన్ ఏంటంటే ఇట్ ఈస్ ఎ ఎనర్జీ ప్రొడ్యూసింగ్ మిషన్. ఓకే, అంటే డిఫరెన్స్ బిట్వీన్ ది టర్బైన్ అండ్ పంప్ లో టర్బైన్ ఏం చేస్తుంది, ఎనర్జీ ప్రొడ్యూసింగ్ మిషన్. ఓకేనా, పంప్ ఏం చేస్తుంది, ఎనర్జీ అబ్జార్బింగ్ మిషన్. ఓకే, ఎనర్జీని తీసుకుంటది అది. పంప్ ఎనర్జీని తీసుకొని వాటర్ ని ఫ్లో చేస్తుంది. ఇక్కడ టర్బైన్ ఏం చేస్తుంది, ఎనర్జీని ఇస్తుంది మనకు, అంటే వాటర్ ని తీసుకొని మనకి ఎనర్జీని ఇస్తుంది. అంటే water energy is converted into the mechanical energy, mechanical energy is converted into the electrical energy means turbine. Okay, పంప్ మాత్రం ఒక ఎలక్ట్రికల్ ఎనర్జీని తీసుకొని మనకు హైడ్రాలిక్ ఎనర్జీని ఇస్తుంది. ఓకేనా, దీస్ ఆర్ ది మెయిన్ డిఫరెన్స్ ఆఫ్ ది టర్బైన్ అండ్ పంప్. ఓకే, నెక్స్ట్ ఇన్ దిస్ చాప్టర్ impulse turbine and reaction turbines. These are the most important. Okay, difference between the impulse turbine and reaction turbine, difference between the pump and turbine sometimes are asked. Okay, impulse turbine, the potential energies are converted into the kinetic energy. Okay, na impulse turbine means potential energy are converted into the kinetic energy. In reaction turbines, fluid is transferred into the kinetic energy before the fluid enters the turbine. అంటే ఓన్లీ ఈ రియాక్షన్ టర్బైన్ లో ప్రెజర్ ఎనర్జీ, కైనెటిక్ ఎనర్జీ ఇస్ అవైలబుల్. ఇన్ దిస్ ఇంపల్స్ టర్బైన్ లో ద ప్రెజర్ ఎనర్జీ ఏమవుద్దంటే కైనెటిక్ ఎనర్జీగా కన్వర్ట్ అవుద్ది. ఓకేనా? ద బ్లేడ్స్ ఆర్ ఓన్లీ ఇన్ ది యాక్షన్ ఆఫ్ ఓకే. అంటే ఇంపల్స్ టర్బైన్ లో నాజిల్ కి ముందే బ్లేడ్స్ యాక్ట్ అవుతాయి. ఇంపల్స్ టర్బైన్ లో నాజిల్ కి ముందు బ్లేడ్స్ ఉంటాయి. రియాక్షన్ టర్బైన్ లో ఏముంటాయంటే ఆల్ టైమ్స్ అంటే బ్లేడ్స్ అనేవి ఆడ వర్కింగే బ్లేడ్స్ మీద డిపెండింగ్ అయి ఉంటది. అంటే ఇంపల్స్ టర్బైన్ ఏంది? పెల్టన్ వీల్ టర్బైన్. పెల్టన్ వీల్ లో మనం వాటర్ అనేది బ్లేడ్ ప్లైకి ఫ్లో చేస్తాం విత్ బై యూజింగ్ ఆఫ్ ఏ నాజిల్. బికాస్ ఆఫ్ నాజిల్ ముందే ఉంటాయంటే బ్లేడ్స్ ఉంటాయి. ఓకేనా? తర్వాత ఈ ఇంపల్స్ టర్బైన్ లో ఫ్లో రెగ్యులేషన్స్ వచ్చేసి వితౌట్ లాస్. అంటే ఫ్లో అనేది వితౌట్ లాస్ లో జరుగుతుంది. రియాక్షన్ టర్బైన్ లో ఫ్లో లాసెస్ పాసిబుల్. అంటే అక్కడ ఫ్లో లాసెస్ అనేవి ఉంటాయి. ఎందుకనంటే అక్కడ వాటర్ అనేది డ్రాఫ్ట్ ట్యూబ్. అంటే వాటర్ అనేది ఎంటర్ అయ్యి హబ్ లోకి వెళ్ళుద్ది. ఇక్కడ హబ్బులు అవి ఏమి ఉండవు. ఈ ఇంపల్స్ టర్బైన్ లో డైరెక్ట్ గా వాటర్ నాజిల్ ద్వారా బ్లేడ్స్ పైన పడిపోతాయి. ఓకేనా? నెక్స్ట్ యూనిట్ యూనిట్ ఈజ్ ఇన్స్టాల్డ్ అబౌవ్ ది టైల్ రేస్. అంటే ఇంపల్స్ టర్బైన్ లో యూనిట్ ఈజ్ ఇన్స్టాల్డ్ అబౌవ్ ది టైల్ రేసు. నెక్స్ట్ రియాక్షన్ టర్బైన్ లో యూనిట్ ఈజ్ కెప్ట్ ఎంటర్లీ సబ్మిటెడ్ ఇన్ ది వాటర్ బిలో టైల్ రేస్. అంటే ఇక్కడ టైల్ రేస్ కి అబౌవ్ ది టైల్ రేస్ లో యూనిట్ అనేది యూనిట్ మీన్స్ పవర్ డెవలప్డ్ యూనిట్. అంటే టైల్ రేస్ కి అబౌవ్ లో ఉంటది. ఇక్కడ ఏంటంటే టైల్ రేస్ కి బిలో లో ఉంటది అన్నమాట. దీస్ ఆర్ ది మెయిన్ డిఫరెన్స్ ఆఫ్ ది ఇంపల్స్ టర్బైన్ అండ్ రియాక్షన్ టర్బైన్స్. ఓకే. మా మెకానికల్ వాల్ కి 4th యూనిట్ ఈస్ కంప్లీటెడ్. సివిల్ వాల్ కి సమ్ పార్ట్ impact of jets are available in the 4th unit. Okay. Next class I can explain the impact of jets. Impact of jets, so hydraulic turbines are also 4th unit in civil engineering. Okay. Only hydraulic turbines also having 4th unit in mechanical engineers. Okay. In this impact of jets is 3rd unit in mechanical. మెకానికల్ వాళ్ళకి 3rd యూనిట్ లో ఇంపాక్ట్ ఆఫ్ జెట్స్ ఉంటుంది. సివిల్ వాళ్ళకి 4th యూనిట్ లో ఇంపాక్ట్ ఆఫ్ జెట్స్ అండ్ హైడ్రాలిక్ టర్బైన్స్ ఉంటాయి. మెకానికల్ వాళ్ళకి 4th యూనిట్ ఓన్లీ హైడ్రాలిక్ టర్బైన్స్.